A solution containing 8.3 grams of non-volatile, non-dissociating substance dissolved in 1 mole of chloroform has a vapor pressure of 511 torr. The vapor pressure of pure chloroform at the same temperature is 526 torr. Calculate the mole fraction of the solute, the number of moles of the solute in the solution, and the molecular mass of the solute. All right. So to begin with this problem, we're going to want to remember Raoult's law. Which states that pressure of the solution is equal to the mass fraction of the solvent times the partial pressure of the solvent. All right. And so for part A, we're interested in the mole fraction of the solvent. And so we're going to just rework this equation here. P of solution divided by pressure of the solvent. Divide this over here by the solvent. And that cancels out. So this is what we're going to be working with for part A. And from here we can just plug and chug. So X of solvent is equal to, and this is given in the solution, 511 torr divided by 526 torr. And those numbers are again given in the problem. All right, and that's when we work out that math, we get 0.971, and that is the answer. For part B, it asks for the number of moles of solute in the solution. So you can think of it this way. So we've got mass fraction of solute plus mass fraction of solvent equals 1. And we know that this is 0.971 equals 1. So subtracting 0.971 from each side gives us solute 0.028 mole. And from there, we're going to solve for the molar mass. And remember, molar mass is always going to have units grams per mole. And they tell us that we have 8.3 grams. And just dividing out, we're working with 0.0821 moles. We can get the molar mass, which will equal 278 grams per mole. And that is the answer for part C. The end.
All right, number 13.66. How many grams of sucrose are needed to lower the freezing point of 125 grams of water by 3 degrees Celsius? All right. So, the equation that we're going to use for this problem is, should be big T, delta T, which is freezing point depression, equals K sub F, molality, so in the problem they give us the lowering of the freezing point temperature, which is 3 degrees Celsius. Table 13.3 in the book gives freezing point and boiling point constants. So we want the one for water, which is 1.86 degrees Celsius for molality. So what is left over is molality, which really is just, can be rewritten as moles of solute over kilograms of solvent, since that's what molality is. And we know what kilograms of solvent is in this equation. We know our kilograms of solvent. We had 125 grams of H2O, which is 0.125 kilograms of H2O. So just using algebra, we can then solve for our moles of solute. So we just times this by 125 over 1.86. Times this side by the same. These cancel out. These cancel out. We're left with moles of solute on this side. And then when you plug all that in to a calculator, you end up with 0.202 for your moles of sucrose. And then the problem wanted the answer in grams. So all you have to do after that is use some conventional analysis. Use the molecular mass of sucrose that you can get from the periodic table. And convert that into moles cancel out, you get grams. You end up with 68.9 grams sucrose, which is the answer.
13.68. A solution of 14 grams of non-volatile, non-dissociating compound in 0.1 kilogram of benzene boils at 81.7 degrees Celsius. Calculate the molecular mass of the unknown. All right. So for this problem, we're going to want to use this equation. Delta T is equal to, and this is Kb, the boiling point elevation, times molality. First of them, I guess. All right. So to start off, we're going to want to find the boiling point elevation, or the change in boiling point elevation. So, and you're going to want to use, again, table 13.3. This is where you'll get the answers, but in the equation, or in the problem, they tell us that we're dealing with 81.7 degrees Celsius, and table 13.33 tells us that the boiling point elevation for benzene is 80.2 degrees Celsius. 80.2 degrees Celsius. Simple subtraction right there gives us a change of 1.5 degrees Celsius. All right, and then also referring to table 13.33, we get the Kb value, which is 2.53 degrees Celsius for molality. All right, and from here we're going to solve for molality. So plugging these values in, 1.5 degrees Celsius is equal to 2.53 degrees Celsius. Molality times molality. So dividing 2.53 divided by 2.53, we get molality to be 0.593 moles of solute per kilogram. In the problem, they tell us that we're actually working with 0.1 kilograms benzene. So, just doing the math there again, we get .0593 moles of the unknown. So, again, molar mass is always grams per mole. And they tell us that we were given 14 grams, and we concluded that we're dealing with 0.059 moles. So simple division there, and we get 240 grams per mole. That's our answer. So give or take significant figures.
All right, 13.70. What are the molecular mass and molecular formula of a non-dissociating molecular compound whose empirical formula is C4H2N? If 3.84 grams of the compound in 0.5 kilograms of benzene gives a freezing point depression of 0.307 degrees Celsius. All right, so for this problem, we are going to use values from table 13.3, and we're going to use the equation for change in freezing temperature equals the freezing point constant times molality. So, in the problem, actually, instead of molality, we're going to write it out as moles of solute over kilograms solvent as well. And you'll see why we're going to do that in a little bit. So I'm just going to plug stuff in. It tells us that the change in temperature we want is 0.307 degrees Celsius. From table 13.3, we can get the constant, which for benzene is 5.07 degrees Celsius per molality. And then over here, moles of solute is what we don't know. And they told us that we were using 0.5 kilograms of benzene solvent. So, I'm just going to use some algebra. I'm going to times on both sides, the times by 0.5 kilograms and 5.07 degrees Celsius per molality on both sides. I'm going to do that. I don't have room, but Same thing over here, it's going to make those cross out. When you do this, you end up with 0.0303 for your moles of the C4H2N compound. This is the empirical formula. So this is the moles, this is the empirical formula. They wanted to know the molar mass. So we know that molar mass is in units of grams per mole. So we know how many, we just calculated how many moles are in our solution, and they told us how many grams. The grams they told us in the problem were 3.84, and the moles we got were 0.0303. So do that math, we get 126.73 grams per mole. So so now to find the molecular formula from the empirical formula, if we calculate the molar mass of the empirical formula, so adding from the periodic table, 12.001 times 4, 1 times 2, and 14, add it all up, you end up with 64 grams per mole. And if you notice that if you double 64, you get 128, which is close to that. So the empirical formula would be this times 2. So, the molecular formula would be this times 2. So the molecular formula is C8H4N2. That's that.
Go. 13.72, Part A. Show that the following equation is true. Molar mass of solute is equal to grams of solute times R times T over osmotic pressure times volume. So I'm just going to write that out so that we can see it. A visual aid there. Oops. JK. Jumping ahead of myself. Wait. Yeah, 5 grams of solid. All right. So for this, just proving it, it's units are going to be our best friend, and that'll just help clarify everything. So again, remember molar mass of solute is always going to be grams per mole. And then so what we'll want to do is just show that all of this right here with the units, when everything cancels out, that we also have grams per mole, and that'll just kind of show that they're equal to each other. So we'll just go over some values really quick. R is equal to 0.0821 liters times ATM per mole per Kelvin. T is just temperature, and that's in Kelvin. Pi is osmotic pressure, and that's given in torrs or ATM. Volume is in liters. So when we plug all of these units back into this equation right here, what we'll end up having is, in grams of solute, grams, obviously. We'll just have grams times ATM per mole per Kelvin, all over osmotic pressure. Cancel, 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 cancel.
Temperature.
Temperature.
Kelvin.
Kelvin. Thank you. Cancel, cancel. There we go. And we're left with grams per mole, which is what we wanted to prove. So that works out perfect. So that's part A. Now we'll go on to part B. All right. And part B says, an aqueous solution of a compound with a very high molecular mass was prepared in a concentration of 2.0 grams per liter at 25 degrees Celsius. Its osmotic pressure was 0.021 torr. Calculate the molecular mass of the compound. All right, so we'll just write down what we know. Concentration, let's get in 2.0 liter. They give us temperature, which is 25 degrees Celsius, which translates into 298 degrees Kelvin. We know osmotic pressure is equal to 0.021 torr. We'll just do a quick conversion into ATM. So 1 ATM is equal to 760 torr. Units cancel, and we're given 2.76 times 10 to the negative 5 ATM. All right, and then again, R value is, that's constant, 0.0821 liters ATM per mole per Kelvin. All right, so now we're just going to use the equation that they give us. Osmotic pressure is equal to mRT, which can also be written as N over V RT, number of moles per volume, molar concentration. And then we want to know N, so we're going to rework this. So N is equal to pi, or osmotic pressure over volume times RT. All right, and then so we're going to do a little plug and chug, just plugging in our values. So osmotic pressure, 2.76 times 10 to the negative 5 ATM. Volume, we know it's 1 liter, divided by 0.0821 ATM per mole per Kelvin. And we're at 298 degrees Kelvin. So we do all of that math right there, we get 1.1 times 10 to the negative 6 mole. All right, and we want molecular mass. Which is going to equal just the mass by moles. And we know that we have 1 in 1 liter. So in 1 liter, we know that we're working with 2 grams, 2.0 grams. And we're going to divide that by the number of the moles that we just found. So 1.1 times 10 to the negative 6 moles. And that gives us our final answer, which is 1.8 times 10 to the 6 grams per mole.
Okay, 13.2 13.74. The vapor pressure of water at 20 degrees Celsius is 17.5 torr. At that temperature, what would be the vapor pressure of a solution made by dissolving 23 grams of sodium chloride in 0.1 kilograms of water, assuming complete dissociation of the solute in an ideal solution? All right, so for this problem, we're going to use the equation used previously in this homework, in this chapter. Partial pressure of solution is equal to our vapor pressure of our solvent times our mole fraction of solvent. So what we're looking for in the equation, or the problem's asking us to find this. It gives us this, and we don't know this. But we can find this from what it gives us. So we need to know the mole fraction. The first thing we need to do is convert everything it gave us into moles. So it gave us 23 grams sodium chloride. Some quick dimensional analysis with the molar mass of sodium chloride, which is 58.44. Gives you the moles of sodium chloride, which was 0.394 moles. Then the moles of water, it gave us 0.1 kilograms, which is equal to 100 grams. So 100 grams of H2O, 1 mole of H2O is 18.2 grams. Grams cancels. We get 5.55 moles of water. So now we know the moles of both. The other thing that we need to consider in this problem is that when sodium chloride is put into solution, it actually breaks up into sodium ions plus chlorine ions. So when you're finding the mole fraction, you need to take into account everything in the solution. So the mole fraction is going to be of water, our XH2O is going to be 5.55 moles of H2O. The part over the whole, so we're going to add our moles of everything up, 5.55 moles of H2O plus, and instead of just 0.394 here, we're going to double that because there's actually two, because it dissociates, you double it because there's two separate things. So doubled, it's 0.788 moles of ions. That's what I'm just going to call it. So that's really Na plus Cl minus. The mole fraction ends up equaling 0.876. So now we know everything for this equation up here, and we can plug everything in to get our vapor pressure solution. We're going to have, it tells us this in the equation, 17.5 torr is the vapor pressure of the water. And then we're going to multiply that by our mole fraction that we got, which is 8.876. And we end up with 15.3 torr. That's the answer.
.76. What is the osmotic pressure in torr? of a 2% solution of NaCl in water when the temperature of the solution is 25 degrees Celsius. All right, so they tell us that a 2% solution of 2% solution of NaCl. So we're going to make an assumption here that we have 100 milliliters of solution, and that, because it's 2%, is going to yield 2.0 grams of NaCl, and we will have 0.100 liters of solution. So, yes, that's important. So, all right, and then from there we're just going to use this equation: osmotic pressure equals MRT. All right, and to find molarity, we're just going to go. We know that we're assuming that we're working with 2 grams of NaCl. And to find the number of moles, we're going to do some dimensional analysis. You know that 1 mole has 58.45 grams. And the grams cancel out, and we're left with moles. Remember, molarity is moles per liter. So if we divide the amount of moles that we get by 0.1 liters, then we'll our molar concentration, which is 0.34 moles. An important assumption here is we're working with NaCl, and so that's going to dissociate, and that's going to give us 2 ions. So what that means is this is going to double by 2 because we have dissociation 2 ions. So times that by 2, and we get 0.68 molarity. All right, and so now that we know what our molarity is, we're going to come back and we're going to plug this into our equation and solve for osmotic pressure. So you know what M is now. So again, pi is equal to M, which is 0.68. R is just a constant, so 0.0821 liters times ATM per mole per Kelvin. All right, and then let's see. All right, and we're going to do just a quick dimensional analysis here. It asks for the osmotic pressure in torr. So really quick, we know that in 1 ATM we have 760 torr. So that's going to cancel, that's going to cancel, and we'll be left with torr. All right, and then next we got T, which is temperature, and that is just 298 Kelvin. So when we multiply across, we get our answer, which is 1.3 times 10 to the 4 torr.
Okay, this is number 13.78. It says, what is the expected freezing point of a 0.2 mol solution of calcium chloride when we're assuming complete dissociation? So, in this, we're trying to find the expected freezing point. So we're going to use the freezing depression equation we've been using. So that's our change in temperature equals our freezing depression constant times molality. The solution we're working with is calcium chloride, which dissociates into calcium ions and 2 moles of chlorine ions. You can just tell that from the way the ions are. So in all there's 3 moles of ions. So we're also going to have to multiply everything by 3 in our problem. So let's just plug things in from what they give us in the problem. We're trying to find our change in temperature. The freezing point, the constant is 1.86 degrees Celsius per molal. The molal concentration is 0.2 molal, and then we have to times everything by 3. That's our Van Hoff factor because of this whole thing. And when we plug all that in, we get our change in temperature to be 1.1 degrees Celsius. So that means that the temperature changes, it gets depressed 1.1 degrees. So this is a water solution. We know that water freezes at 0 degrees Celsius. So that's our initial freezing point. We want to find the final. We know how much it depresses, so if we just do this, we just subtract, then we end up with negative 1.1 degrees Celsius, which is the new freezing point for that solution. And that is the answer.
.80, the Van Hoff factor for the solute in 0.1 molality nickel sulfate is 1.19. What would this factor be if the solution behaved as if it were 100% dissociated? So right now they're saying that it is 1.19 is the Van Hoff factor. But if it dissociated 100% and we're dealing with nickel sulfate, then if that dissociated, we would have nickel 2. And because we have 2 ions, the factor would be 2. That is the answer.
13.82. A 0.118 molal solution of lithium chloride has a freezing point of negative 0.415 degrees Celsius. What is the Van Hoff factor for this solution at this concentration? So this problem is dealing with freezing points. Again, so we're just going to use that same equation we've been using. That's right, 13.82. Okay, we're going to use that same equation we've been using all night. That's this one. And they want to know what the Van Hoff factor is, so we're going to add that in to the equation. It tells us that the solution is a solution in water, so though we know the constant, we get that from table 13.3. So the constant is 1.86. They also told us in the problem our concentration in Molar. Still looking for I. It also told us that the freezing point of the solution is negative 0.415 degrees Celsius. Since it's a solution in water, the change in temperature is going to be the freezing point of water, which is 0 degrees, which is 0 degrees Celsius minus the freezing point, so it's initial minus final, and that's going to give us our change in temperature. So if we do that, then it's positive 0.415 degrees Celsius for our change in temperature. So when we just divide on this side by these two numbers, they're going to cross out. I'm going to divide on this side by the same thing. And that is going to leave us with I. So that all in the calculator gives us 1.89 for our Van Hoff factor for lithium chloride. I can't remember what thing it's for, but that's the answer. All right.